Example 9 deals with a different form of heat transfer called conductivity. That's where there's no contact between the hot surface and the cold surface. This is different than what we've done so far, in the sense that up till now there's always been contact between the hot surface and the cold surface. The power, or the rate of conductive heat transfer, is given by P, which is minus little k, known as the thermal conductivity, times A, which is the area, times the change in temperature with respect to distance now. Yeah. Sometimes this is written as dq dt, but keep in mind that capital T now is temperature, not time. So if we use this formula, we can say that the power is K A dt is going to be T hot minus T cold. I forgot the minus. Over dx is just some distance, let's call it d, between the hot and cold surface. So now we can say that P equals minus Ka Th minus Tc over d. So a picture of this would be is that you have the hot surface here, a cold surface here, and there's some distance d between them. Yeah. And there's an area that's associated with this system. We are told that the thermal conductivity is 0.01 watts per meter times degrees Celsius. The area of the box that we are dealing with is 0.95 meters squared. There's a change in temperature from 35 degrees, which is the hot surface, to 0 degrees, which is where we have the ice. All over the distance of the walls is 2.5 centimeters thick. So if we do this, we find out that this comes out to about 13.3 watts. And if we look at the formula that P equals dq over dt, we know that from our math skills we can rewrite this as delta q over delta t for certain properties, and we can generalize that this is just the ratio from the energy over temperature. So the energy itself is going to be the power times time. This is time, not temperature, sorry. So if we take our 13.3 watts and we look at 1 day, which is the time, the day has 24 hours, and there are 3,600 seconds per hour. That will give us 1.15 times 10 to the 6th joules of energy. So the energy associated with melting the ice then is going to be, like we've looked at before, the mass of the ice times the latent heat of fusion for ice, which means that the mass of the ice is the energy for melting the ice over the latent heat of fusion for ice. The energy associated with melting the ice is what we just found, the 1.15 times 10 to the 6 joules. And then the latent heat of fusion for ice is the 334 times 10 to the 3rd joule. And if we do that, we get about 3.44, sorry, kilograms. So let me just fix this a little bit here. This should be 3.44 kilograms.